equivalent. They are equivalent, right? So the first one is the definition, linear independence. Actually, it is just the statement about vectors even through Vm are linearly independent. So what does that mean? According to the definition, so here is the second statement. So these vectors, none of them is redundant. Okay, that's the definition, right?
Yep.
Okay. So you know how to find identify the redundant ones. Go from the left to the right, right? So first one, if it is non-zero, then it's not redundant. Then you go to the second, the third. So in fact, here they did not review the redundant definition. Instead, in the third statement, it is rephrased. The definition of a redundant vector is Vi is a linear combination of the preceding ones, right? But here in this third statement, it says none of the vectors Vi is a linear combination of the other ones, so including the preceding ones and then the ones that are after, right? So it turns out these two are equivalent in linear combination of the previous one is equivalent to being a linear combination of all other vectors. So it requires some argument, but it's not too difficult to see why this is true. Now this time we use relation. So in particular, relations, some of them are trivial. Actually, one of them is trivial, which is always there. You give me any vectors V1 through Vm or in Rn, then we can always use the 0 as the coefficient. So 0 times 1 plus 0 times the second plus all the way 0 times Vm is going to be 0, but that's the trivial one. They are not interesting. The question is whether there are non-trivial ones, right? Relations. That means whether you can find C1 through Cm, not all 0, such that you have this relation, right? So in terms of this relation, linear independence is equivalent to the only relation among this V1 through Vm is the trivial one, right? That means you can close, sorry, I was going to say close your eyes, right? Or just rephrase it. Because I was going to say, you close your eyes and then write down. It's hard, right? So how about we say, without thinking, just write down C1 V1 plus C2 V2 all the way Cm Vm, and then set it to 0. If you can show the only way for this to be true is C1 equals C2 equals Cm all the way 0, right? So the first part is without thinking. You don't need to think. You ask me, so one way to consider linear independence or dependence. One way of doing this is this. You give me a set of vectors, V1, V2, V3, say 3 of them, M is 3. You ask me whether they are linearly independent or dependent. So I'm going to, without thinking, write down C1V1 plus C2V2 plus C3V3, and then still without thinking, set it to 0, right? Now the hard part is to show that whether this C1, C2, and C3 must be all 0. Or somehow you can find C1, C2, C3 not all 0. Still this is true, right? So these two cases. So that's in fact, in many textbooks, that's the way of doing it, right? So just set it up as a relation and then see if you can show all these coefficients must be 0. But that is equivalent to solving AX equals 0. What is A? The matrix, this is A. How about this? A. The matrix A is, okay, is the matrix of what? The columns are the vectors you give me. You give me V1, V2, V3. I use them, V1 as the first column, V2 the second, V3 the third, okay? To form this matrix. So that would be A. A times X equals 0 is equivalent to this one. Why? So can you tell this one? This relation with C1, C2 all the way Cm there. That's unknown. We don't know them, right? We just remember without thinking. Some of you may be able to do it with closed eyes closed, right? It's right straight. So you write it down. This is the same or equivalent to this matrix times C1, C2 all the way Cm equals 0. So let me reinforce this by just writing it down, okay? C1, V1, how about I do it for 3? So this part, we just do it without thinking, right? Set this up. Now the left-hand side is V1, V2, V3, 3 columns. And this is the matrix A times C1, C2, C3 equals 0, 0, 0. That is A. How about still call it X? This is the X, right? C1, C2, C3 are unknown. So that's the X. This is the A and equals 0. So AX equals 0, that means X is in the kernel of A, right? AX equals 0, so kernel. So that is why in the fifth statement, they say C1, C2 all the way Cm must be 0. Is equivalent to this kernel only has one element in it. That's the 0 vector. See, this is a set notation, right? A pair of braces and then you put 0 in there. 0 vector. So that means X must be 0 is equivalent to the kernel of A. Kernel of A has only one vector in it. So kernel of A has only 0 in it. Okay? So that's the fifth statement. Okay? Over there. Okay, now what happened in terms of the rank? Rank of A. Rank of A, so that's the sixth statement. Rank of A should be equal to M. Why these two, fifth and the sixth, are equivalent? Well, this says AX equals 0, X must be 0, right? Okay, so that means unique solution. Trivial solution is the only solution, right? Of AX equals 0. So that means there are no free variables, right? No free variable means what? This is rank R. M minus R is 0. 0 means what? No
Free variables.
free variables.
Which means for every.
So what happens if you have free variables? I can set it as t, right? How about a particular t equals 1? Then I solve for the leading variables, right? Then you will have a non-zero or non-trivial solution, C1 all the way through Cn. One of them is not 0. Because I already set 1 to be 1, right? So C1, C2, C3. If one of them is free variable, I will set a value 1 to it. I wouldn't set a 0 to it, right? Because I want to find a non-trivial relation. So that is one. Why? We have the sixth statement. So all these are equivalent. So I think it's good to spend a few minutes to review this table, okay? Okay, so let's go to 3.3. The title is the dimension of a subspace of Rn. So we go to say R3, R4, R5. We already know the subspaces will be a line through the origin, a plane through the origin in R2 and R3, right? Things like that. And the R3 itself and the zero set. How about the dimension? We already know what dimension is in R2, so dimension is 2. In R3, dimension is 3. But how about if I give you a subspace V in Rn or R3, R2, okay? What is the mathematical definition of the dimension? So it is defined to be the dimension. See, we go to the next page to find the definition. So the definition says, consider a subspace V of Rn. The number of vectors in a basis of V is called the dimension of V, using this notation, DIM, parentheses, and V, right? So here, let's go to this sentence. Here, in a basis. So the implication is in any basis. So it doesn't have to be a specific one, just take anyone. So in order to have a well-defined concept, we have to justify. We have to show that all the bases, no matter which one you use, right? All bases contain the same number of vectors. So the basis vectors, you will have 2 in a 2-dimensional subspace. You take any basis, you count how many vectors in it, it's going to be 2. Right? You cannot find 3. So I'm talking about 1. Subspace V. You already found a basis, and you count, you find 2, right? Then someone else present another basis. Then without counting, I already know it should be 2. Now this common number then is used to define, to be defined as the dimension. So the prerequisite for doing this is we need to show in every basis the number of vectors is the same. So that's why we need to go back to do something. So basically, so I'm going backward. So the problem is to justify all basis of a subspace V, so same subspace V of Rn. So you find any basis consist of the same number of vectors. So you take any basis, count how many vectors in it. By the way, they are called the basis vectors. Then you will have the same number, no matter what basis you are counting. So why? So this is a theorem. That means it is something to be proved. Okay? So how do we prove this? So let me give you an outline. So basically, you have to show that if you have two bases, and these two bases, remember what is the definition of basis? They span V, right? And they are linearly independent, right? So the basis, so I have basis 1, how about that? And then basis 2. So that's what they say in the argument. So suppose one basis has V1 all the way Vp in there. V1, Vp, three of them. So these vectors are all in Rn. Say V is subset of Rn. This is a subspace. The other one, W1 through WQ. Q them. We want to show P equals Q, right? So show P equals Q. They must be the same. And this common number, then is the dimension, right? Now, the way to do this is, first of all, these span. They span V. So these also span V, right? Another condition is these are linearly independent. Here, W1 through WQ also are linearly independent, right? Okay, so then we use this condition, we can show that they have the same number, P and Q are the same, okay? So how do we know this? So we go back to it, right? In fact, we could have done this in a simpler way. We can just say definition here, and then are you convinced? If you say I'm convinced, then we can stop. We don't need to go backward, right? Okay.
Not convinced.
I think it's good to have some justification outline, right? Why this is good. So along the way, we learn one thing. When you say in a basis without any explanation, then this basis is any, right? After any basis. Then a natural question. So in mathematics, very often, when you make a definition, people ask, is this a well-defined definition, right? Well-defined in this case means you need to justify that. All bases have the same number of vectors in it. So that's that theorem, okay? And then we could have just stopped here and then say, if we are convinced, we move on, right? But then let's just do a little bit more. So that's, this theorem is the basis for the proof. So what we're doing is, we're going to show P is less than equal to Q. So that's another good thing to know, right? In mathematics, how do you show two are equal? One way of doing this is, first, you show P say is less than equal to Q. So suppose I can do that. Based on these two basis information about the vectors, right? Suppose I can prove one way, P is less than equal to Q. If I can do this, so in fact, this is the thing I need to do. if I can do this, then the second part is automatic, or it follows from this. Why? I can turn around and say, well, how about we switch the order? This is named basis 1, right? Now, how about we call this basis 2? This is basis 1, right? Then we repeat. Well, we'll just use this result. We'll know Q will be less than equal to P, right? If you switch, call this first, that second, right? So from these two, then you will get P must be equal to Q. There are only 3 possibilities, right? Either less than or greater than, or they are equal. So that's the outline. So that's why we need to focus on this. So the way to focus on this and then get this inequality is to observe this second basis. The vectors in there span. So they span, right? So since they span this V, so every vector V1, say, is going to be, how about I use C1V1, C1W1, CQWQ. So each one is a linear combination of these ones, right? Because they span, right? And these vectors are in it. So every one can be rewritten as, how about I use W1 as the first column, and then WQ as the last column, times C1 and then CQ. So that's what we did often. Remember, you have a linear combination. I can rewrite this as a matrix, right? Times a column vector. Okay, then from here, they call this B, and then they call this U1. So V1 is B times U1. And then one thing we can do is, we do this for all of them. VP is then B times UP. V1 through VP is B times, so how about B times U1? Next, I use this V1, V2, all the way VP to form a matrix. So using them as the columns, right? Columns, form this. So this one is equal to, remember V1 is BU1. So they are too far away, B times U1. So I'm going to replace V1 by BU1. And then VP by BUP. And then I can pull out the B. So pull out the B, and then U1, UP. Now in the book, if you want, you can read the book. They call this A, matrix A, and then this is B, and they call this C. So A is equal to B times C. So what is A? You use V1, VP as columns, that's A. You use W1 through WQ as columns, you get the P, right? This is B. And then you have this U1 through UP, the coefficients in that. C1 through Q. So coefficient is a vector, so we call it U1. So U1 through UP, that's C. And then they argue that C times X equals 0 if C times X equals 0, then BCX also equals 0. That means if X is in the kernel of C, in kernel of C, then X is in the kernel of A. Why? Because AX and A is BC, so AX is B times CX. So if X is in kernel of C, that means CX is already 0, right? Then B times, no matter what B is, B times CX is also 0. That means X is in kernel of A. But kernel of A, what can we say about kernel of A? That's in the summary here. So that's why I review this. Kernel of A. This is kernel of A, right? V1 through Vm. Here M is P, right? V1 through Vp. In this statement, we have V1 through Vm. We are talking about this one, right? We are not talking about two bases. So V1 through Vm are linearly independent. Remember, they are basis vectors, right? So they are Li. Being Li, what do we have? The kernel of A, this would be A, is 0. That means, so let me put this in here, that's 0. So Cx, that means X in the kernel, then X must be 0. So that means C kernel of C is also 0. Alright, so this statement is based on this. If X is in the kernel of C, that means Cx equals 0, then B times 0 is 0. That means this X must be 0. That means C, the kernel of C is 0. Okay? Now, we'll use this again. Kernel of this is 0. What can we say about the rank? So here comes to the rank. So we have how many columns? P of them, right? V1 through Vp here on this statement number 6. V1 through Vp. So V1, V2, how about V3? P equals 3. So we have P equals 3. And then now, what happens if the kernel of C needs to be 0? So that means the rank. So rank, I'm sorry, so I already changed to U1 because V are used for A, right? Matrix A. Here we are talking about matrix C. So that's matrix C. U1, U2, and U3. So this is rank 0. So how about this? Let me just point out that in the book, when they prove this theorem up there, they use the fact that you have this condition A equals B times C to show that the kernel of C is 0. And therefore, when they quote theorem 3.1.7, okay, that means Q must be greater than or equal to P. So that theorem 3.1 is actually summarized as this 6 rank. There's a rank relation. So that means the number of leading ones after you write this matrix as RREF. You count how many leading ones. The leading ones, the number equals m. So in that case, you get the matrix cannot be one that looks like this. More columns than rows. It must be like this. Okay? And that is why we should have P less than equal to Q. Okay? If you use the linear independence property of basis 1 and use the spanning property of basis 2, then you will get P less than equal to Q. Then you turn around, switch the rows, right? The ordering, then you will get Q is less than equal to P. Therefore, they are the same. Okay? So I'm not going to require full from this, understanding the whole thing, but you get an outline, right? And then you realize that we do need to work on something. So well-defined things, the problem needs to be well posed. Right? Okay. So now let's turn to the question of properties. So here in this theorem 3.3.4, we talk about independent vectors and spanning vectors in a subspace of Rn. So you give me a V, a subspace of Rn. Then we have, say, a number of independent vectors. So we have some vectors and we know they are linearly independent. So can we have some information about the number of these linear independent vectors? So to put it in the R2 or R3, the simple cases R2 and R3, say R2. Can you find 3 linearly independent vectors in R2, right? So the answer is no. If you can find 3, then what happened? The dimension of R2 would be what? Would have been greater than 2, would be 3 at least, right? Because you have one basis, these 3. You already find these 3. So the dimension will be at least 3. Okay? So that's why they say we can find at most m linearly independent vectors if the dimension is m. So if the dimension is 2, you can only find at most 2 linearly independent vectors. So if you give me 3, and then say, figure out whether they are linearly independent or not, then we should right away answer the question, right? What will be the answer? So let me repeat the question. I give you 3 vectors and tell you they are linearly independent. And we are in R2, right? Each one of these vectors is in R2. I give you, sorry, let me rephrase it. I give you 3 vectors and I ask you, are they linearly independent? So these vectors, 3 of them are all in R2. Then you immediately say, no, right? They are not linearly independent. Why? Dimension of R2 is 2, so m is 2 in that first statement. You cannot find more than 2 linearly independent vectors. You can find 2 at most, right? Okay. B, we need at least m vectors to span this subspace V. how many vectors you need to span R2? At least 2. Well, you need 2. If 2 span, then you can add some other vectors, right? You can even add 0 vector. You can add any other vectors. If you have 2 vectors that span R2, then you can add more. But at least you need 2. So that's what they said in the second statement. How about C? If you find m vectors, so dimension is m, remember? Dimension of V is m. And then what happens if you find m linearly independent vectors? What can you say about it in terms of spanning or not spanning V? If you find m of them, then they form a basis. Why? Because m vectors linearly independent, they must span. They will. They span. So because the number is correct, you already have m of them, right? You need at least m of them to span. And then I do have m, right? And they are linearly independent, so they must span. And then therefore they form a basis. Okay, how about the other way? If I already have m vectors, they span. M already span. Then what can we say about these m vectors? They form a basis as well. Why? Because these m vectors, they must be linearly independent. Okay? Otherwise, if this set of vectors is not linearly independent, then one of them can be deleted. Then you don't have enough number. Remember, we at least need m of them. So you cannot have one deleted and still span the whole thing, right? So this part is consequence of this B. We need at least m vectors, right, to span this subspace B. So if you already have m of them, then they must be, if they span, then they must be linearly independent, therefore form a basis. Otherwise, we can delete one. So there will be, at least one of them will be redundant. Then we can delete that one. You will have less than m vectors still span a subspace V of dimension m. That's contradicting part B. So they prove all these are so all these 4 statements in this paragraph. So I'm not going to